In the macroscopic world, angular momentum is highly intuitive. We see it in a spinning gyroscope, a pirouetting ice skater, or a planet rotating on its axis. We understand physical objects turning through three-dimensional space. But that intuition completely fractures when we zoom down to the atomic scale. The trouble started in a laboratory room in Germany in 1922 with the Stern-Gerlach Experiment. Researchers fired a beam of electrically neutral silver atoms through a strongly inhomogeneous magnetic field. Instead of smearing out randomly, the beam split perfectly in two. Half the atoms deflected up and half deflected down. This proved that electrons were acting like tiny, distinct magnets. Physicists measured this property and found it perfectly matched the mathematical equations we use for angular momentum. Because the math looked like rotation, they gave this property a simple name, spin. Applying that physical, macroscopic word to a quantum phenomenon created a massive misunderstanding of physics that we are still fighting today. If we treat an electron as a physical sphere, calculating its required rotation reveals a problem. Given its tiny size, the surface must spin faster than light, violating relativity. To fix this, physics defines the electron as a dimensionless point particle with zero spatial volume. But that introduces a stark geometric reality. A dimensionless point does not have a physical surface, and it cannot possess an axis of rotation. If an electron has no physical size, and attempting to rotate it breaks the speed of light, then quantum spin must be something entirely alien to our concept of motion. We have to separate two concepts. Orbital angular momentum involves actual movement through physical space, like an electron circulating around a nucleus. Intrinsic spin is an internal, fixed property of the particle itself, existing regardless of movement. Mathematically, quantum mechanics uses a spinor. Rotate a spin 1/2 particle 360 degrees, and it inverts. It requires a second full rotation, 720 degrees, to finally realign. This shows spin is a topological twist, not a rigid body. The standard Copenhagen interpretation of quantum mechanics asks us to accept this as a brute mathematical fact. We are taught to use the label spin while completely divorcing it from any physical reality. Does that mean absolutely nothing is moving inside an electron? A growing ontological debate is challenging that idea. Philosopher of physics Charles Seibbons points out that the rigid point-particle model might be the problem. Instead of an infinitely tiny dot, field theory treats the electron as a spread-out, continuous wave of energy and charge localized within the Dirac field. Under this framework, you don't need a solid sphere rotating on an axis. Spin is generated by the literal, circulating flow of energy and charge within the field itself. The electron is actually moving. But we have to discard the idea of a solid object spinning like a top, and instead picture the continuous, organic circulation of a quantum field. Whether you favor abstract topology or circulating fields, this invisible, microscopic property dictates the macrostructure of the universe. Governed by the Pauli exclusion principle, particles with half-integer spin are forbidden from occupying the exact same quantum state. They are repelled into distinct slots. Without this restriction, these stacked electron shells would fail. Every electron would instantly collapse into the lowest energy level. This spin-enforced separation is the sole reason atoms possess volume. It allows chemical bonds to form, molecules to stabilize, and solid matter to exist. We can interpret it as a purely mathematical spinor, or as the physical circulation of a subatomic field. But this strange, non-classical twist is the foundational architecture holding our reality together.